The merits of schemas. As we saw, protocol buffers, Thrift, and Avro all use a schema to describe a binary encoding format. Their schema languages are much simpler than XML schema or JSON schema, which support much more detailed validation rules, e.g., the string value of this field must match this regular expression, or the integer value of this field must be between 0 and 100. As protocol buffers, Thrift, and Avro are simpler to implement and simpler to use, they have grown to support a fairly wide range of programming languages. The ideas on which these encodings are based are by no means new. For example, they have a lot in common with ASN.1, a schema definition language that was first standardized in 1984. It was used to define various network protocols, and its binary encoding DIA is still used to encode SSL certificates X.509. For example, ASN.1 supports schema evolution using tag numbers, similar to protocol buffers and Thrift. However, it's also very complex and badly documented, so ASN.1 is probably not a good choice for new applications. Many data systems also implement some kind of proprietary binary encoding for their data. For example, most relational databases have a network protocol over which you can send queries to the database and get back responses. Those protocols are generally specific to a particular database, and the database vendor provides a driver, for example using the ODBC or JDBC IPs, that decodes responses from the database's network protocol into in-memory data structures. So, we can see that although textual data formats such as JSON, XML, and CSV are widespread, binary encodings based on schemas are also a viable option. They have a number of nice properties. They can be much more compact than the various binary JSON variants, since they can omit field names from the encoded data. The schema is a valuable form of documentation, and because the schema is required for decoding, you can be sure that it is up to date, whereas manually maintained documentation may easily diverge from reality. Keeping a database of schemas allows you to check forward and backward compatibility of schema changes before anything is deployed. For users of statically typed programming languages, the ability to generate code from the schema is useful, since it enables type checking at compile time. In summary, schema evolution allows the same kind of flexibility as schemaless/schema-on-read JSON databases provide schema flexibility in the document model on page 39, while also providing better guarantees about your data and better tooling. Modes of data flow. At the beginning of this chapter we said that whenever you want to send some data to another process with which you don't share memory, for example, whenever you want to send data over the network or write it to a file, you need to encode it as a sequence of bytes. We then discussed a variety of different encodings for doing this. We talked about forward and backward compatibility, which are important for evolvability, making change easy by allowing you to upgrade different parts of your system independently, and not having to change everything at once. Compatibility is a relationship between one process that encodes the data and another process that decodes it. That's a fairly abstract idea. There are many ways data can flow from one process to another. Who encodes the data, and who decodes it? In the rest of this chapter we will explore some of the most common ways how data flows between processes. Via databases, see Dataflow Through Databases on page 129. Via service call, see Dataflow Through Services, REST and RPC on page 131. Via asynchronous message passing, see Message Passing Dataflow on page 136. Dataflow Through Databases. In a database, the process that writes to the database encodes the data, and the process that reads from the database decodes it. There may just be a single process accessing the database, in which case the reader is simply a later version of the same process. In that case, you can think of storing something in the database as sending a message to your future self. Backward compatibility is clearly necessary here, otherwise your future self won't be able to decode what you previously wrote. In general, it's common for several different processes to be accessing a database at the same time. Those processes might be several different applications or services, or they may simply be several instances of the same service running in parallel for scalability or fault tolerance. Either way, in an environment where the application is changing, it is likely that some processes accessing the database will be running newer code and some will be running older code, for example because a new version is currently being deployed in a rolling upgrade, so some instances have been updated while others haven't yet. This means that a value in the database may be written by a newer version of the code, and subsequently read by an older version of the code that is still running. Thus, Forward compatibility is also often required for databases. However, there is an additional snag. Say you add a field to a record schema, and the newer code writes a value for that new field to the database. Subsequently, an older version of the code which doesn't yet know about the new field reads the record, updates it, and writes it back. In this situation, the desirable behavior is usually for the old code to keep the new field intact, even though it couldn't be interpreted. The encoding formats discussed previously support such preservation of unknown fields, but sometimes you need to take care at an application level, as illustrated in Figure 4-7. For example, if you decode a database value into model objects in the application, and later re-encode those model objects, the unknown field might be lost in that translation process. Solving this is not a hard problem, you just need to be aware of it. Except for MySQL, which often rewrites an entire table even though it is not strictly necessary, as mentioned in schema flexibility in the document model on page 39. Figure 4-7. When an older version of the application updates data previously written by a newer version of the application, data may be lost if you're not careful. Different values written at different times. A database generally allows any value to be updated at any time. This means that within a single database you may have some values that were written 5 milliseconds ago, and some values that were written 5 years ago. When you deploy a new version of your application of a server-side application, at least, you may entirely replace the old version with a new version within a few minutes. The same is not true of database contents. The 5-year-old data will still be there, in the original encoding, unless you have explicitly rewritten it since then. This observation is sometimes summed up as data outlives code. Rewriting migrating data into a new schema is certainly possible, but it's an expensive thing to do on a large dataset, so most databases avoid it if possible. Most relational databases allow simple schema changes, such as adding a new column with a null default value, without rewriting existing data. When an old row is read, the database fills in nulls for any columns that are missing from the encoded data on disk. LinkedIn's document database Espresso uses Avro for storage, allowing it to use Avro's schema evolution rules. Schema evolution thus allows the entire database to appear as if it was encoded with a single schema, even though the underlying storage may contain records encoded with various historical versions of the schema. Perhaps you take a snapshot of your database from time to time, say for backup purposes, or for loading into a data warehouse. See data warehousing on page 91. In this case, the data dump will typically be encoded using the latest schema, even if the original encoding in the source database contained a mixture of schema versions from different eras. Since you're copying the data anyway, you might as well encode the copy of the data consistently. As the data dump is written in one go and is thereafter immutable, formats like Avro object container files are a good fit. This is also a good opportunity to encode the data in an analytics-friendly column-oriented format such as Parquet. See column compression on page 97. In Chapter 10 we will talk more about using data in archival storage. Dataflow through services, REST and RPC. When you have processes that need to communicate over a network, there are a few different ways of arranging that communication. The most common arrangement is to have two roles, clients and servers. The servers expose an API over the network, and the clients can connect to the servers to make requests to that API. The API exposed by the server is known as a service. The web works this way. Clients' web browsers make requests to web servers, making GET requests to download HTML, CSS, JavaScript, images, etc., and making POST requests to submit data to the server. The API consists of a standardized set of protocols and data formats: HTTP, URLs, SSL/TLS, HTML, etc. Because web browsers, web servers, and website authors mostly agree on these standards, you can use any web browser to access any website, at least in theory. Web browsers are not the only type of client. For example, a native app running on a mobile device or a desktop computer can also make network requests to a server, and a client-side JavaScript application running inside a web browser can use XML HTTP requests to become an HTTP client. This technique is known as AJAX. In this case, the server's response is typically not HTML for displaying to a human, but rather data in an encoding that is convenient for further processing by the client-side application code such as JSON. Although HTTP may be used as the transport protocol, the API implemented on top is application-specific, and the client and server need to agree on the details of that API. Moreover, a server can itself be a client to another service. For example, A typical web app server acts as client to a database. This approach is often used to decompose a large application into smaller services by area of functionality, such that one service makes a request to another when it requires some functionality or data from that other service. This way of building applications has traditionally been called a service-oriented architecture (SOA), more recently refined and rebranded as microservices architecture. In some ways, services are similar to databases. They typically allow clients to submit and query data. However, while databases allow arbitrary queries using the query languages we discussed in Chapter 2, services expose an application-specific API that only allows inputs and outputs that are predetermined by the business logic application code of the service. This restriction provides a degree of encapsulation. Services can impose fine-grained restrictions on what clients can and cannot do. A key design goal of a service-oriented/microservices architecture is to make the application easier to change and maintain by making services independently deployable and evolvable. For example, each service should be owned by one team, and that team should be able to release new versions of the service frequently without having to coordinate with other teams. In other words, we should expect old and new versions of servers and clients to be running at the same time, and so the data encoding used by servers and clients must be compatible across versions of the service API, precisely what we've been talking about in this chapter. When HTTP is used as the underlying protocol for talking to the service, it is called a web service. This is perhaps a slight misnomer because web services are not only used on the web, but in several different contexts. For example, a client application running on a user's device, for example a native app on a mobile device, or JavaScript web app, using AJAX making requests to a service over HTTP. These requests typically go over the public internet. One service making requests to another service owned by the same organization, often located within the same data center, as part of a service-oriented/microservices architecture. Software that supports this kind of use case is sometimes called middleware. One service making requests to a service owned by a different organization, usually via the internet. This is used for data exchange between different organizations' backend systems. This category includes public APIs provided by online services, such as credit card processing systems, or OAuth for shared access to user data. Roman 6. Even within each camp there are plenty of arguments. For example, HTOA's hypermedia as the engine of application state often provokes discussions. Roman 7. Despite the similarity of acronyms, SOAP is not a requirement for SOA. SOAP is a particular technology, whereas SOA is a general approach to building systems. There are two popular approaches to web services, REST and SOAP. They are almost diametrically opposed in terms of philosophy, and often the subject of heated debate among their respective proponents. Roman 6. REST is not a protocol, but rather a design philosophy that builds upon the principles of HTTP. It emphasizes simple data formats, using URLs for identifying resources and using HTTP features for cache control, authentication, and content type negotiation. REST has been gaining popularity compared to SOAP, at least in the context of cross-organizational service integration, and is often associated with microservices. An API designed according to the principles of REST is called RESTful. By contrast, SOAP is an XML-based protocol for making network API requests. Roman 7. Although it is most commonly used over HTTP, it aims to be independent from HTTP and avoids using most HTTP features. Instead, it comes with a sprawling and complex multitude of related standards, the Web Service Framework, known as WS*, that add various features. The API of a SOAP web service is described using an XML-based language called the Web Services Description Language, or WSDL. WSDL enables code generation so that a client can access a remote service using local classes and method calls, which are encoded to XML messages and decoded again by the framework. This is useful in statically typed programming languages, but less so in dynamically typed ones. See code generation and dynamically typed languages on page 127. As WSDL is not designed to be human-readable, and as SOAP messages are often too complex to construct manually, users of SOAP rely heavily on tool support, code generation, and IDEs. For users of programming languages that are not supported by SOAP vendors, integration with SOAP services is difficult. Even though SOAP and its various extensions are ostensibly standardized, interoperability between different vendors' implementations often causes problems. For all of these reasons, although SOAP is still used in many large enterprises, it has fallen out of favor in most smaller companies. RESTful APIs tend to favor simpler approaches, typically involving less code generation and automated tooling. A definition format such as OpenAPI, also known as Swagger, can be used to describe RESTful APIs and produce documentation. The problems with remote procedure calls RPCs web services are merely the latest incarnation of a long line of technologies for making API requests over a network, many of which received a lot of hype, but have serious problems. Enterprise Java Beans EJB and Java's remote method invocation RMI are limited to Java. The distributed component object model DCOM is limited to Microsoft platforms. The Common Object Request Broker Architecture CORBA is excessively complex and does not provide backward or forward compatibility. All of these are based on the idea of a remote procedure call RPC, which has been around since the 1970s. The RPC model tries to make a request to a remote network service look the same as calling a function or method in your programming language. Within the same process, this abstraction is called location transparency. Although RPC seems convenient at first, the approach is fundamentally flawed. A network request is very different from a local function call. A local function call is predictable and either succeeds or fails, depending only on parameters that are under your control. A network request is unpredictable. The request or response may be lost due to a network problem, or the remote machine may be slow or unavailable, and such problems are entirely outside of your control. Network problems are common, so you have to anticipate them, for example by retrying a failed request. A local function call either returns a result, or throws an exception, or never returns because it goes into an infinite loop where the process crashes. A network request has another possible outcome. It may return without a result, due to a timeout. In that case, you simply don't know what happened. If you don't get a response from the remote service, you have no way of knowing whether the request got through or not. We discuss this issue in more detail in Chapter 8. If you retry a failed network request, it could happen that the requests are actually getting through, and only the responses are getting lost. In that case, retrying will cause the action to be performed multiple times, unless you build a mechanism for deduplication idempotence into the protocol. Local function calls don't have this problem. We discuss idempotence in more detail in Chapter 11. Every time you call a local function, it normally takes about the same time to execute. A network request is much slower than a function call, and its latency is also wildly variable. At good times it may complete in less than a millisecond, but when the network is congested or the remote service is overloaded, it may take many seconds to do exactly the same thing. When you call a local function, you can efficiently pass it references pointers to objects in local memory. When you make a network request, all those parameters need to be encoded into a sequence of bytes that can be sent over the network. That's okay if the parameters are primitives like numbers or strings, but quickly becomes problematic with larger objects. The client and the service may be implemented in different programming languages, so the RPC framework must translate data types from one language into another. This can end up ugly, since not all languages have the same types. Recall JavaScript's problems with numbers greater than 253, for example CJSON, XML, and binary variants on page 114. This problem doesn't exist in a single process written in a single language. All of these factors mean that there's no point trying to make a remote service look too much like a local object in your programming language, because it's a fundamentally different thing. Part of the appeal of REST is that it doesn't try to hide the fact that it's a network protocol, although this doesn't seem to stop people from building RPC libraries on top of REST. Despite all these problems, RPC isn't going away. Various RPC frameworks have been built on top of all the encodings mentioned in this chapter. For example, Thrift and Avro come with RPC support included. gRPC is an RPC implementation using protocol buffers. Finagle also uses Thrift, and REST.li uses JSON over HTTP. This new generation of RPC frameworks is more explicit about the fact that a remote request is different from a local function call. For example, Finagle and REST.li use futures promises to encapsulate asynchronous actions that may fail. Futures also simplify situations where you need to make requests to multiple services in parallel and combine their results. gRPC supports streams, where a call consists of not just one request and one response, but a series of requests and responses over time. Some of these frameworks also provide service discovery, that is, allowing a client to find out at which IP address and port number it can find a particular service. We will return to this topic in request routing on page 214. Custom RPC protocols with a binary encoding format can achieve better performance than something generic like JSON over REST. However, a REST-full API has other significant advantages. It is good for experimentation and debugging. You can simply make requests to it using a web browser or the command line tool curl, without any code generation or software installation. It is supported by all mainstream programming languages and platforms, and there is a vast ecosystem of tools available: servers, caches, load balancers, proxies, firewalls, monitoring, debugging tools, testing tools, etc. For these reasons, REST seems to be the predominant style for public APIs. The main focus of RPC frameworks is on requests between services owned by the same organization, typically within the same data center. For evolvability, it is important that RPC clients and servers can be changed and deployed independently. Compared to data flowing through databases as described in the last section, we can make a simplifying assumption in the case of Dataflow Through Services. It is reasonable to assume that all the servers will be updated first, and all the clients second. Thus, you only need backward compatibility on requests and forward compatibility on responses. The backward and forward compatibility properties of an RPC scheme are inherited from whatever encoding it uses. Thrift, gRPC protocol buffers, and Avro RPC can be evolved according to the compatibility rules of the respective encoding format. In SOAP, requests and responses are specified with XML schemas. These can be evolved, but there are some subtle pitfalls. REST-full APIs most commonly use JSON without a formally specified schema for responses, and JSON or URI-encoded/form encoded request parameters for requests. Adding optional request parameters and adding new fields to response objects are usually considered changes that maintain compatibility. Service compatibility is made harder by the fact that RPC is often used for communication across organizational boundaries, so the provider of a service often has no control over its clients and cannot force them to upgrade. Thus, compatibility needs to be maintained for a long time, perhaps indefinitely. If a compatibility breaking change is required, the service provider often ends up maintaining multiple versions of the service API side by side. There is no agreement on how API versioning should work, i.e. how a client can indicate which version of the API it wants to use. For REST-full APIs, common approaches are to use a version number in the URL or in the HTTP accept header. For services that use API keys to identify a particular client, another option is to store a client's requested API version on the server and to allow this version selection to be updated through a separate administrative interface.